Don't.
All right. Hi, everybody. Welcome to seminar this week. I'm Sarah Jones, same as last week. This week we are going to talk about the art of going small, and we have the honor of having Professor Hugh Miller present this talk for us. He's been president of SME. He's had 60 short courses throughout the industry. He's a great honor to have him here as our professor. He's been a professor at U of A. He's done 13 years in different mining companies and different positions, from operations to corporate management. Yeah, so he's a great honor.
Sure.
Sorry.
No big deal. No, you did good.
Okay.
It's a real pleasure to be here. And what we're going to talk today about, and I'm trying to stay in the right slot here. What we're going to talk today about is some of the water jet work we've been doing, the hydro-excavation systems. We're going to talk about specific applications, and then we're going to go into two case studies, that one of which is close and near and dear to my heart, which has to do with confined space excavation, primarily associated with narrow vein mining. And so, again, the idea is what can we do to improve or to rectify some of the major challenges that we're facing. And so let's, can everybody hear me? Okay, cool. So the whole concept of water jet technology has been around forever. And so it dates back until the early 1850s, in the Comstock area of Western Nevada. And during that period of time, and then in Eastern California, during that time, it was used for placer gold mining. So the essence were we used giants, and these are big hydraulic monitors that exist. And they would go and they would flush down material, they'd break it up, and then you put it through sluices or through what used to be called hydraulic tunnels. That you line a tunnel full of mercury, and then the sediments would flow through it, and you pick up the gold. These are two relatively recent photos in the last 5 years. The upper one is using big hydraulic monitors with dragline operations for phosphate. And so what they do is they pick up and they mine phosphate with the dragline, swing it over, put it into basically what it is, it's almost like a big sump. And then what they do is high pressure jets, they break it up, and so they can pump it into a slurry. And then they send it to the plant. This is in Minnesota. They're mining frac sands that are used for fracking in oil wells and gas wells, for dilating fractures and stuff. So you have to have certain sizes of sand that's got certain angularity to it, certain size fraction. And again, it's more cost effective to actually mine it with water. And so the concept's been around for a long, long time. In fact, if you go outside this door and look on the wall, there's a water jet dredging system that's currently being used to mine ilmenite in Australia. There's approximately 6 to 8 million tons of coal mined a year with high pressure water. And the concept's been around for a long time. So what we're going to do is we're going to talk about some of the dynamics of how this works. How we got involved with water jets, it's kind of an interesting story, but kind of puts things into perspective. So in 1988 and 89, a million years ago, before most of you guys were born, I was working for a precious metal mining company, and we were working on an exploration project in which we were underground. It was a brownfields project, and we were sinking shaft and driving ramp, and we were developing a couple of levels for test stopes for bulk sampling. And as mine superintendent, it's just tons of work going on. But I came in after hours one time, and we had this long tunnel that's 2,800 feet long. And on this tunnel, we had a bunch of these little teeny veinlets. And again, I walked in off hours, walked down. I was just wanted to see how the crews were doing on the weekend. And when I got to one of these veinlets, it was a rolled over, there was free, visible gold, free gold in a gouge of the structure, just maybe 6 inches wide, but rolled over. So it had a dip of like 40 degrees. And so you look at this thing and, it was obvious that the miners were using bull hoses with water to flush this stuff out. And then they were collecting it up in their lunch boxes and taking it home to pan out. And of course, for a mine, you don't want that occurring in off hours, right? You want the miners to be focused on what they're supposed to be doing. So we came in and we shotcreted over the top of it and all that stuff. But before we did that, myself and the guy I was working for, Paul Jones, and a couple other geologists, we sat down because this vein that intersected this tunnel, we also had drilled into it, about 500 feet higher than us, and we had drilled into it some 1,000 feet on strike. So it was a pretty sizable resource. But the problem is, again, it's half a foot, 4 inches, rolled over, 40 degrees, bad angle, right? And so we try to calculate, it was going, someplace in the range of 15 to 20 grams per ton. Pretty decent grades, but not great. The problem, again, it was visible gold. So we try to figure out how you could figure that out, how we could make it work, look at a whole series of different types of minimum mining widths, try to figure out what it is that we could actually drill it out and then blast it down in a kind of a sub-level stoping system. Just couldn't figure out a way to do it. And so again, we closed it up to prevent miners from getting inside because we're really concerned about the hanging wall coming down. And so as a consequence of that, I remembered as an undergrad here that Fun Wong and the guys at EMI were doing work with high pressure fluid for excavation purposes. And as an undergrad, I worked up at the school mine, and we had done some work for Fundin up there as well. So I took some time off, came down, talked with Fundin at depth and some of the guys from EMI. And there was a group that left Earth Mechanics Institute to form their own company called Stone Age. And that group, they were producing water jet equipment. So water jet was a pretty relatively new industry. The first high pressure pumps ever produced was by a couple of Boeing engineers up in Seattle in the early 70s. And ironically, EMI bought the first 2 pumps they ever produced, ever built. And so Fundin and the group, John Wagamont, Jerry Sink, and a bunch of others at EMI actually were pushing that technology pretty hard. At the time, the pumps were horrible. There were no accessories. There were rigid pipe, no flexible tubing, nothing like that. And so a lot of development was occurring. And so I'm in the late 80s during this period of time. So I spent time with Fundin and I learned a bunch of stuff. I went over to Missouri Rolla and spent a week with Dave Summers, who was doing a lot in the area of water jet technology. Spent time down in Durango with the Stone Age folks. And then I went down to Texas, and there was another gentleman that created a company around water jets. And the more I learned, the more I realized, man, there's huge potentials. And again, having an underground background, particularly from Eastern Washington, Northern Idaho, where we have lots of vein structures, minimum mining widths are huge for the costing of these operations. Vast majority are uneconomic because you just can't, labor productivity and the waste that are generated because of dilution, you just can't live with it. So I saw it as a venue potentially going forward. And that's when I made the decision to come back to work on a PhD supported by a water jet company and proceeded from there. So what we're going to talk about is a lot of different things that have been done here as well as in other places in terms of research around this technology. Pretty simple stuff in terms of the overall general dynamic. When we start talking about hydro-excavation or water jet systems, it just means it's a way of creating, conveying, and directing fluid energy to do productive work. And so in this case, creating, we can create pressure. We can do pumps or cannons, extrusion devices, all sorts of different things we can use. In fact, we can actually use elevation, natural head, right, to generate pressure. The way to convey it to wherever we want it to go, well, it used to be only pipes. Now we have flexible hoses that'll go to 70,000 PSI. So we have a whole range of accessories to be able to do some things. We have hoses and tubing and flow and pressure control. So we have all this stuff to be able to divert streams in different ways. And then we have ways to direct that energy, namely nozzles, swivels, motion control systems, all of that stuff that comes about. So again, most of this stuff was invented in the 70s and 80s. And it was truly a novel technology at the time. Relatively young. The problem was most of it was looked at in construction and mining. If you looked at the universities that were involved with water jet technologies in the 70s and 80s, mines, Missouri Rolla, Alabama, when they had a mining program there. They were primarily LSU, primarily excavation oriented focused universities or mining universities. And so what came out of that, you know, again, mining was a big part of this until the 80s. And then the rest of the world found the technology. And then basically what happened was the technology is now being utilized in every manufacturing sector you can imagine. You sit in your car, everything you see in your car has been cut with water. Your shoes, if you're wearing, vast majority of tennis shoes are all cut with water. Every paper product produced in this country is cut with water. It's used for, you know, with abrasive jets, we can cut any material. So carabiners, made of titanium, cut with water. All sorts of different things. We won't go through these applications, but the big fields have developed in the 80s, 90s, and 2000s has been in the cleaning industry and corrosion removal. The other part of that is we look at you know, assemblies with concrete excavation and bridge decks, marine fouling of ships, all of that stuff, and that's actually grown a big part of that. But the petrochemical plant industry, when we look at heat exchangers, heat exchanger bundles, the cleaning of those, piping networks, sewer cleaning, just goes on and on. So when we look at applications across the board, but we still do an awful lot of work looking at the excavation side. But this is a number I always find amazing. Despite the technology now being almost 40 years old, it's still growing by 20% per year. And so it's truly amazing by the number of applications that are occurring repetitively. So this is a couple things, right? This fiberglass food, you know, if you ever canned soup and stuff, all the vegetables and meats are all cut with water or glycerin. It's widely used to cut a variety of different types of foods. Graphite, really effective way. We can turn a jet on, start a cut in the middle of a panel, and we can end it that way. We don't have any shock loading that we normally would have with other types of materials like glass and things like that are really sensitive to it. And then we can, you know, for deflashing, when you cast these things with helmets and a variety of fiberglass parts, you know, the toppers on canopies for pickups and stuff, they actually form them so you have a complete thing all the way around them. You cut open the openings with a water jet. So real common applications. Aircraft are real common. You know, again, cleaning, piping networks. This is a stand that cars, when they paint the cars, they put cars on a stand and it goes into a paint bath. And they're removing all the paints that accumulate on that stand. Complicated gearing, and we can actually put abrasives into the flow to allow us to cut any metal. And again, 100% of paper products are cut with water in this country. The thing is toilet tissue and things like that is cut so fast that it doesn't have time to absorb the water. Why would they use water jets for paper? Why would you do that? Cheap. Cheap is a good one, but there's a real second one. What happened when they used knives?
Accurate and powerful.
What's that?
Accurate and powerful.
Yeah, you know, dust explosions, right? Health issues, things like that. So everything went to convert to that. Guy, you know, a buddy of mine graduated from here, did a lot of work in water jets. He's now working on putting systems together for disposable diapers. You realize that's $1.5 billion industry in North America by itself. It's a huge thing, but it's all cut now with water. So pretty amazing stuff in terms of the span of applications. Ship cleaning, marine fouling. One of the big things that happens because you're worried about marine growth is the substrate on ships are now coated with a chromite finish. The problem with chromite, it's poisonous. And so you don't want to use sandblasting because that stuff gets liberated, and particularly when you're near the ocean, when you have workers doing it, it creates problems. So now those outer marine coatings are all removed. Bridge decks, we do it, and we'll go back through why that's done, because we've done some variations off of that. And then heat exchanger bundles, it's all automated processes. Used to take weeks and weeks and weeks to clean these bundles and get the precipitates out of the tubes. Now we can do it in a matter of hours remotely with water jet systems. So why do we like water jets? The attractive thing is I can focus thousands of horsepower if I want over a very small area. Remember Newton's third law? What is that? Newton's third law? Impacts everything we do in the mining business.
Action reaction.
Yeah, for every action, there's an equal and opposite reaction, right? So when we start doing drilling, right, weight on bit is an important component, as is torsion, right? Torque. So the issues with that is, for me to drill fast, I have to have a lot of weight on the bit. But if I do that, I get reactive forces coming back, so my drill rigs have to be big. They got to be robust in order to handle the reactive forces that are coming off of that. Why is a TBM designed the way it is with so much mass? Same reason, right? So we look at the amount of force we're putting in, particularly with big cutters. We got to have the ability and rigidity in the system to be able to take care of the reactive stuff. Great thing about water jets, do we have direct mechanical contact with the rock? No, we don't at all. So the only reactive forces we have is from the flow rate of the fluid that's coming out of the orifice of the nozzle, okay? Which is a fraction of what it is. So we can have highly flexible systems that are easy to design, motion control systems for it, and we don't have those big reactive forces. It's continuous operation, unlike drill blast and muck type systems. No direct rock contact, omnidirectional. What's that mean? Are mechanical excavators generally considered omnidirectional? Yeah, usually you want to align it with the direction of whatever your hammer is on a jumbo, or whatever the control arm is, right? You want things going in a proper direction with the mass of the machine. Water jet can go in any direction and it doesn't make a difference. Okay? We don't have the same reactive forces that are created within the system. Pretty simple, highly flexible. We can change on the fly how we move it, the flow rates. We can change the pressure. It's real amenable to remote control. We don't generate any dust or gases as a part of that. This is a question mark, and this we've done some research here looking at whether it's truly not an ignition source. And there's some reasons why we're going through that, and that's still an active area of research we're doing here. It's highly selective, again, very small jet. I can actually be selective about what I excavate, mobile, and we can adapt it to a lot of different types of geology. That said, there's some issues associated with it, right? So a couple of the things, one of the big things, when we start talking about water jet, it actually encompasses a big umbrella of different types of technologies. The problem with continuous round jets is that there are a lot of different variables that dictate productivity. And so it's not just, you know, flow and pressure, but it's how the nozzle is designed, the configuration of the system, the way we energize the fluid, whether there are pulses within the fluid itself, the aerodynamic drag within the stream, as well as the friction that develops within the system. There's issues about flow modulation, which means there's internal dynamics happening within the flow, how we move the jet, how the energy is developed. And there's some 42 different variables that dictate jet operations. And so this is the reason when people will say, well, we tried cutting this rock and it didn't work. Well, the question is what are you cutting it relative to what structure? Some of the issues we have, right? So continuous jets, the problem is there's so many variables, and you got to look at the internal fabric of the rock, and then you have to dial up one of those variables that meets that stuff. And although we use matrix to try to figure out and minimize the selection, it's still a pain in the neck. And it takes a long time to empirically come up with data. And the problem is sometimes it's not repeatable. One of the things we often will do with students is they'll take a block of granite and ice from the Edgar, and we'll put 10,000 PSI on it and just leave the jet. And we'll run it for a few minutes, and it won't even mar the rock. But then we move the jet at the same pressure relative to the rock structure, and we tear it apart. And the reason is understanding how the jet works relative to the rock fabric. And there's so many, because there's so many variables involved, there's been a lot of work to look at alternative types of water jet systems. So how many of you are familiar with cavitation? Yeah, we've spent billions of dollars, industry has, on trying to reduce cavitation, right? Minimize it, pump propellers of ships, particularly in submarines, all sorts of stuff like that. We're trying to minimize the dynamics of the formation of cavitating bubbles. Turbulence causes vapor pressure to develop with these bubbles, and when they collapse, they create microjets, instantaneous high pressure events that when they impinge against the system, they'll erode anything. And if you've ever eaten up a titanium impeller on a pump by cavitating, it's incredible. You can eat up an impeller in seconds. And it's just because the dynamics of how these things work. Now, instead of trying to prevent it, we're trying to encourage it, right? And we're also trying to control it. So these cavitating clouds are incredible in terms of the production of energy as they impinge against surfaces. You can erode almost anything. The problem is how do you develop a stable cavitating cloud and get it outside your nozzle without it destroying your nozzle? That always becomes the issue, okay? Another type is, these are pulse jets. And pulse jets, what we're doing here, and I did my PhD on these things back in the 90s. I worked for a company. We've spent, over the last 10 years, probably $5 million in the development of these things. What these things are is, imagine taking a ball peen hammer and impulse loading, but we're doing it fast. And so we're now developing these pulses with a frequency that approaches the resonant frequency of rock. So we're well over 12,000 hertz. And what happens is the flow is going so fast, the mass of these slugs are such that when they impinge against the surface, they cause flexing, plastic deformation within the surface of the rock. And when we hit resonant frequency, things fall apart. And so just as compared with continuous jets, a magnitude increase easily in most cases, for most rock types. But the problem is we still have the same problem. This is with a strobe light, but the same problem we have is trying to keep these systems together. And we've done it in a lot of different ways. For cleaning, the idea is we fatigue off layers of different types of paints and coatings. But again, real promising thing, but still a ways to go. This is kind of the holy grail, the work that's being developed, particularly in the geomechanics part of the thing. We now have abrasive jets. They were invented in the early 80s by flow research and fluidine systems. In that case, what we're doing is we're transferring the momentum of the water through an orifice against an abrasive, usually corundum like garnet. And then we're transferring that energy to the garnet. The garnet then hits whatever the target is, and the garnet does the work, and it liberates stuff. And that's abrasive jet cutting is what we use for metal cutting and all sorts of other stuff. Well, the problem with abrasive jet cutting, it requires ultra high pressures of the water. So we're operating between 40 and 60,000 PSI. And now we're getting into the range where, this is pretty significant in terms of cost and the types of equipment we have to have. In this case, this jet is only 4,000 PSI. But instead of having a system where you pressurize the water and then inject the abrasive in to a mixing tube under Venturi and having the energy transferred to the abrasive and then the abrasive goes out of mixing tube, instead we're pumping the abrasive in the fluid to pressure. And the reason that works out better is if we're injecting the abrasive in, the momentum gets transferred, the abrasive stays on the outside of the stream. It's not uniform all the way through. And then we fracture about half of it, because you can imagine the abrasive is going from 0 miles an hour to 6,000 feet a second, right? So we're just shattering some of this stuff. In this case, we're pumping the abrasive in the fluid such that we don't have to go very high. The abrasive is uniform across the stream. It works really effectively in cutting almost anything. And again, look at this is part of the curve that was cut. Goes right through the aggregate, goes through the matrix, works out well. Clean cuts, provides all sorts of different venues. Problem is, as you can imagine, we're putting the abrasive and the fluid. What happens to the nozzle assembly and the hoses and the pump and everything else? Just destroys it. And so right now there's a couple of companies that have working prototypes. The lives are horrible, a couple hours. Whereas, everybody's doing research and developing this, because if you make it work, you're going to be a gazillionaire overnight. So pretty cool stuff. So we've looked into a lot of those technologies here at Mines, but these are, in recent times, these are the things that we've looked at. We've done metal cutting in explosive environments, particularly both with hydrogen and a variety of different types of methane. The idea is for us to be able to do hot work. If you've ever heard of hot work, it's where you're using cutting torches or other types of welding in highly explosive environments. It creates an explosion, kills 5 to 6 people a year. So are there substitutes for cutting metal in these environments, particularly can we do it remotely? And that's what Eric Cherrier did. That focused on them. We had a project for a number of years working for Newmont on confined space excavation, narrow vein mining, primarily at the Midas operation. And that went very well. And again, that was a build off of some work that I did during my thesis, as well as for another company. Dredging and marine excavation, we'll talk more about that a little bit later. That was Chris Wyatt's project. We were looking at the redesign of rotary suction heads to try to eliminate some of the problems with dredging. Blast hole drilling and stope slotting, sublevel stoping, you have to have something to blast to, right? So rather than using drop raises, which is always an issue, you actually excavate out an area that you can actually blast to in these stopes. Remote excavation, concrete and soil, that's a big topical area, particularly with construction around underground utilities. And hydro-scaling and scarification, we did that up the mine. Great results. We'll talk more about that here in a second. And then comminution, fine grinding. And we've done a couple of experiments, probably 4 or 5 theses have been done on comminution here at Mines over the years. So, in terms of water jet excavation, mechanical assist, this is kind of the bread and butter of EMI back in the 70s, 80s, and early 90s. We outfitted tunnel boring machines, both with Robbins and with Worth, and did in-quarry testing of those. The roadheader to the right was done by Mike Hood at the University of California, Berkeley. Now he's more recently at the CRC in Australia. And the idea, again, is in these situations to use mechanical water jet assist. The water jets actually will help fragment material, but it'll also get rid of the ground up material that sits underneath the bits itself. But again, the intent is to be able to use mechanical excavators for harder material. And it's, again, a continuous excavation process. Reactive forces are minimal. And again, there's certain things mechanical excavators do that are great. Certain things, not so much. Irregular shapes, types of radius in terms of turns, things like that. And so, and small excavations that don't have the ability to amortize costs over a big rock volume. And so in those situations, there needs to be an alternative system. Drill and blast, we have problems with that in a lot of different applications. particularly in urban excavation. So again, this is viewed as a kind of a niche technology for some of this stuff. Oh, a good example of that. I was just thinking, you know, do you guys, any of you ever been to St. Louis? St. Louis Arch? Yeah. Did you go in the museum underneath the arch?
Of course, yeah.
Yeah, pretty cool, right? And so when they built the arch first, and then they had the idea of putting the underground museum in, right? So what they had to do is they had to reinforce the underground part underneath of the arch. You can imagine tunnelling under the arch coming down, right? So they put a huge number of caissons. And because they did that, they couldn't drill and blast because of concerns related to impairing the rock mass. And they couldn't use a mechanical excavator because the rock was too hot. Plus you had all these caissons all over the place, right? So it was excavated using a type of abrasive jet for that entire volume. And that's a huge, huge room underground. And so those are types of applications where it makes sense. Okay? Couple things, drilling systems, lots of different types of drilling systems have been put together. A lot of these things that we've done here at Mines, Muthu, you remember that? It's sitting on one of the tables down there. That was part of a water jet system for drilling rapidly in oil and gas deposits. But again, there's lots of different types of applications. We're working on some stuff with rock bolting and use of cable bolts and stuff like that. Hydraulic scaling, we did this up at the mine. It was under a NIOSH grant, 2 NIOSH grants actually for scaling, and then 1 for rock scarification. So one of the problems with scaling is that mechanical scalers in real mines, the problem is you can almost dig with them at times. And so it becomes problematic. The other problem with them is you gotta have flat floors. You can't drive up on muck piles. The other problem with that is that these things are big, right, and expensive, and you got to be careful as you're scaling. You're not creating more damage into the rock mass than you're actually knocking material down. So that's one thing. So we came up with some systems for using water jets to actually scale loose rock down. There's actually, based on our work, there are now 2 commercial firms doing that in Canada. Also, rock scarification, the idea is rather than having to put bolt and mesh and then shotcrete over the mesh, the idea is that there's ways that we can rough up the ribs in the back in such a way that the shotcrete would adhere to it better. And we went through that process as well, and it was wildly successful. So kind of cool things. The idea is for improving safety elements. This was Chris White's program. We got a patent out of this. Because some pretty cool ideas. So if you look at dredging systems, huge industry for keeping waterways open. It's also finding more and more favor in the mining industry because you can have a 2 people operating the dredge, and you can pull 1,200 tons an hour out of some of these systems. So one piece of equipment loads directly onto a conveyor system or into a piping network. You know, if you have access to water, it allows you to do a lot of different things. We focused on the rotary suction dredges. This is a problem primarily from the civil construction side. As these big dredges go around, they rotate, and they've got pretty aggressive teeth on them. And then there's a suction hole inside it. And so as these things go around, the harder the material there is, the faster you spin the head. Well, the problem is that as the cuttings come out, centrifugal force throws these things out. And you end up with this big sediment plume that follows these things. And there's big environmental implications to it in places like the Columbia River where you have endangered salmon. And so in this case, we came up with this idea of putting in an insert for water jets. So as the head rotates in one direction, we create a vortex going in the other. And what happens is it constrains the sediment dispersion and actually loads and creates a higher slurry density going into the machine. And so it actually goes back into the machine and we get better capture of material. So part of the idea behind this was not only again civil construction, but there's a lot of mining applications that might make sense to using this kind of technology because of the productivity associated with it. And that extends well beyond gemstones and diamonds and things like that in Namibia and other places. Other things that we've worked on here, I don't know, Yasser has been gone now 7 years. So, but what he did was we had a system, we were working with a company that was mining phosphate underground. And the problem is using borehole mining, using large diameter jets. Problem is we could expand the cavity faster than removing all the material. And so what would happen is the cavity got big, would collapse. And so mining recoveries were real low. And so as a consequence of that, we had capabilities of designing these cavities in any way we wanted. But we needed to come up with a plan of how to do that. So Yasser came up with an analytical way of trying to design these cavities that corresponded with an operating strategy. And so we could try to maximize recovery from these things. And it was successful, and the company is still using that algorithm. And then dimensional stone cutting is a big market, particularly in certain parts of the world like Turkey. So when we look at mining these blocks, the idea is you drill holes in and then you put expansive grouts in them or things like lime that expand when you seal or add water. And then that creates, basically splits the rock in tension. The other way to do that is with big saws, big radial saws, and not very practical for big blocks. And then diamond impregnated wire saws. And pretty dangerous. They use them up at Marble, Colorado. If any of these things ever breaks, it's catastrophic. Highly dangerous, logistically hard to work with. And so a company called NetJet initially started this process of mining these big blocks with water. And then we started working with them on looking at using abrasives and other things to create very nice curves. And again, it's actually Hamelman sells, I don't know, 20 or 30 of these units a year around the world for mining these blocks. So what I thought we would do in the remaining time is talk about two project examples that we've recently done here that was pretty neat projects. The first had to do with hydro-excavation and shotcrete liners from tunnels. And this was supported by the University Transportation Center for Underground Transport Infrastructure. It was also supported by Ramex Inc., which is a waterjet technology company. Scientific Associates, we use their waterjet lab for the most part, and IET Waterjet Foundation, which is a foundation that was set up here by Fund and Wong. But when we start talking about issues associated with shotcrete liner failures, this is both mines and underground construction, even though this project was focused on underground construction. There's a lot of reasons we end up with liner failure. Water, people running into the ribs, that sort of thing. Motion, in high stress environments where you get motion within the underground workings. There's a lot of things that happen. Water inflow, particularly if it's got sulfides in it, reacts with the binders in both the shotcrete and the concrete and fails. And sometimes, and again, it's just high stress. So in these cases, we have all sorts of things that happen on these types of tunnels because both in shotcrete and concrete. So how do we fix them? Well, we can bring in big excavators that come in, and they can have disc cutters on them, or they can have tooth cutters, just like a rotator, and they just grind up the stuff associated with the shotcrete or the liner itself. What happened? Do we normally have steel in that stuff? Yeah, so what happened? How well does a pick cutter do against rebar or rock bolts? Bad things happen, right? Particularly with stuff failing. Again, problems with pneumatic or hydraulic scalers, mechanical scalers, gotta have flat floors again. But man, when you start hammering into stuff, the rebar that's normally in it reverberates. And also the substrate, the rock that it's attached to, vibrates. And it vibrates at a different rate than the liner. And so you get separation, we call it delamination. And so you get delamination to the steel structure, as well as between the cement and liner and the grout, and then usually the rock substrate. And so it creates a mess. And so in those cases, when you start excavating, you have to end up excavating a whole entire unit out, because as you remove the part that's damaged, you're messing up the parts that are next door to it. And so you have a propagation effect of problems that you have to, in order to fix, you have to remove. And if stuff's high, you've got to come in with manlifts, right? Cherry pickers to go in. And now you're operating off a platform that could be 40 or 50 feet off the ground. And that's not a good thing. So have any of you ever been on an elevated platform before? Yeah. So what do you tie off to? Yeah, exactly. Particularly when you're using a pneumatic drill, the thing is just shaking all over the place. Where do you tie off to? Tie off to the back that's way off the ground? To a bolt? You could do that, but if you fell, you'd be hanging from the back, right? Normally you tie off, you use your fall suppression system to the basket. So what if the basket goes over? It's going to drag you with it. So the fatalities and injuries associated with this kind of thing is huge. And so because of that, it's not a real pleasant way to go. And so there needs to be an alternative for it. So what we came up with is the ability to use water jets to excavate that stuff. But the question we had to answer was, what's the vibration that we're going to impart to the rebar? Okay, that's part of the issue. As we excavate this stuff using impact hammers versus using a water jet system, are we going to see delamination occur? And are we going to see separation of the rebar? Are we going to see vibrations occur? And so what we did was we created test panels, created a whole slew of these things. So put in steel, the rebar, 3/8 rebar is the same type that we would see in most types of shotcrete applications. We use the same steel density that you would see conventional designed liners. And what we did was we used the same composition of both concrete substrate with the rebar that's in it, and then we put wire mesh down, and then we added a shotcrete coating to it. Okay, so we had a multi-layered impact, and we had the proper amount of steel that would be consistent with what you'd see in industry. So with that, we went through, we had instrumentation to measure vibration and accelerometers off the rebar itself, so we can measure the vibration of things. We also looked at ground penetrating radar so that we could actually look at delamination as it occurred between both the rebar and the liner, as well as the substrate versus the shotcrete. And so the idea for us was to be able to look at that and be able to remotely characterize that. So the first part of that was to actually use an impact hammer to go through and excavate a certain amount of material, created a total mess down at poor EMI during this process. But in doing so, we asked the students, if at all possible, to try not to hurt the rebar, okay, or the wire mesh. In both cases, it got pretty much destroyed just simply because of the process of the hammer. The other thing that we saw is we get microfractures that develop along where the wire is and the rebar is, as well as along areas where the impact hammer went out and just splayed out fractures into the substrate. And so this is a typical look, and this is looking at one area, and this is the fractures that developed along the boundary. So we had total delamination that occurred. So then we took the same blocks and put a water jet system in there, and this is the instrumentation and schematic of the jet. So in this case, we used a rotating 2-orifice continuous jet operated at 28,000 psi, approximately 6.5 GPM. And what we did was we put just a simple linear motion system that we could raise and lower. We put a sample on a lift table and instrumented it with data acquisition system with a high pressure pump. We had a centrifugal pump to pressurize that. And then we had a water tank where we recycled some of the water coming back. Pretty straightforward system. And so this represents the the water jet lab that we did it at. And you can see, as we excavated back and forth, it created a very nice slot. But the main thing in here is see the seal? It just cleaned it. It didn't dent it. It didn't alter it. We didn't end up with peripheral fractures that developed out of it. So it was a great improvement over the mechanical stuff. Also, again, nice clean edges for the most part. Okay, we didn't have issues associated with ragged elements or stray fragments or cracks. And this is the big thing. So this is the vibration analysis that occurred with mechanical impact hammers. This is the vibrations that occurred during the water jet. And what we did was we used a filter for this to try to create the same amount of time that was put together to make it equate to the productivity of both. And so you can see, obviously, hardly any vibration that occurred at all because of the water jets. And so because of those two things, we put a recommendation in. These shows GPR data, shows delamination that occurs between the substrate as well as with the rebar, and that we saw using mechanical excavation. Pretty cool thing. Next step in this, we put a proposal in to DOT for doing more excavation of this type for tunnels, and hopefully we'll hear back. I don't know. Jamal put it in, so probably 3 or 4 months, maybe. Well, hopefully we'll get it funded. Next steps. Second project, and this is the one that's close to heart. This was funded by Newmont, and we had a number of collaborating companies, including Cellular Robotics, Scientific Associates, IET Waterjet, and NLB Waterjet Systems. So the idea here, think about narrow vein mining. Going back to that example I talked about, monovein. The problem was just, you have these logistical elements about mining in confined space. Minimum mining width, minimum mining height are huge, right? We start looking at alternative mining systems for narrow vein stuff. It's hard to justify normally a sand plant for cut and fill operations, although we can use run-of-mine muck. That's fairly common. But normally when we look at the mining methods we're using, our shrinkage, we're going to use some sort of variation of cut and fill. Some narrow vein mines, like at Midas and a couple of the smaller operations in Nevada, have started using sublevel stoping. But the problem is the dilution at Midas was in excess of 500%. So that means you have 5 times more waste that you're mining than ore. So the economics fall apart. Why it worked at Midas was they were able to do bulk mining activities using LHDs and jumbos and mine at a rate where they could tolerate the dilution because of the high value of the ore. Very unusual circumstance where that occurs. But again, when you start looking at direct labor costs, you look at both for shrinkage and underhand cut and fill, you're over 65% labor costs. So you got to figure out a way to get rid of the labor component. And the other part of that is labor productivity, right? So if we look at double-breasted backstoping in a cut and fill operation, we're looking at 15 to 20 tons per man shift. Not very much, not very many tons. And so if you're a mine that has 1,000 tons a day, that means you're going to have 20 to 30 operating stopes. That also means, because some of them will always be down for maintenance or for the fill part of the cycle, means you have to have another 10 stopes of where you can cycle to. Now you've got issues just like the Lucky Friday, where you have 400 or 500 people now in order to be able to do all the stuff that you have to do in terms of development and production for 1,000 to 1,200 tons a day. And that's why you're looking for these automated systems. It's why the Lucky Friday and Hecla are looking at the new vein mechanical excavation system for trying to eliminate, the large dependence upon skilled labor in these operating environments. So when we start looking at this stuff, the big things are, you got to have, mechanisms that you minimize dilution. It's got to have good labor productivity. The costs have to be decent, but the problem is we're not producing enough ounces or pounds of material to amortize the cost of these methods. So it's a big problem. Permitting and regulatory compliance for small mines is a big issue. Financing and cash flow constraints, it's huge. That's a big thing. And then when we start looking at processing, access to processing facilities, how many, this is always a kind of an interesting one. If you're a small mine, you're producing 500 tons a day, which isn't all that small, right? And you produce maybe a 30-to-1 concentration ratio for your sulfides. So if you look at that, you're producing less than, easily less than 10 tons of cons a day, right? And so that means you're going to send out 1 rail car a week of concentrates to a smelter. It's hard to find smelters that are going to want to accept that small of deliveries. And so normally you'll be forced to sell it to someplace in Latin America to do that. So again, continuous problems with being a small mine. Other things, with these things, we have health and safety implications. Again, dependence on labor. One of the guys, is a well-known fixture in the Silver Valley. He was a mine manager of Bunker Hill when the Sunshine Fire happened. He came back, reopened Sunshine, and ran that mine for another 15 years. Harry Kaufler is his name. It's just a legend in the hard rock business in the U.S. But he brought up a good point one time. He said, underground hard rock mining is the only industry in the world where we're putting individuals underground to do strenuous work that's highly predicated on their own, their own judgment, their insights and their capabilities. We're putting them in a dark environment that's over 100 degrees at 100% humidity. Again, it's dark, right? And we're requiring them to be productive. And their productivity directly impacts our profit. When you start thinking about those dynamics, something's got to change, particularly when we're paying miners now as a minimum $250 to $300 a day. And then we look at labor costs associated with indirect stuff, right? Health insurance and all the rest of that stuff. And so we're paying underground miners in these kind of applications well more than what we're paying engineers. So normally 100 to 150,000 a year. The issue with that is that you can't be an underground miner in these applications after the age of 40. You just get broken up. And so because of the impact of that, you gotta find an alternative. You gotta find a different way. And so that's the motivating issue in this. So the concept is, let's mine at the economic margins of the structure. Okay, let's mine inside the vein. Let's not mine using minimum mining rates. If the structure is 6 inches, we mine at 6 inches. And how do we do that? Well, one of the concepts is using hydraulic excavation. We can mine down to 2 or 3 inches if we needed to for the structures. And there's different ways of using the motion control systems and all of that. We went through the process of designing this for Midas, for Newmont Midas. Unfortunately, about halfway through this project, Newmont sold Midas. And so, and Hollister was the other property we were looking at. Problems with that sale kind of critiqued this stuff, but we kept going because of these other partners we have to come to a solution. But again, looking at the kind of the overall dynamics of this, it works out good. If we mine it narrow, we may not need to use fill. We might allow the stopes to collapse on their own because there's not enough displacement to get filled up pretty quickly. So this is one of the systems, what it looked like. So we had a frame that actually had grippers on the side. This was the original design of it. We had grippers on the side. We had a motion control system that was hydraulic that could go back and forth and up and down. And the idea was to put it, suspend it in a stope. And at the very top, all we're doing is we're punching in a bunch of bolts and we're creating a trolley system between the bolts. And in this case, then we can have this apparatus go forward and backward. We mine in a vertical prox. we're gonna actually use a rock box, something that we do in construction, right? Great. And so this is the status of this project and how it worked out. Economics looked good, and it all became a motion system. So, and again, you can build something like this for less than $400,000. So this is the end of the talk. Thank you very much. I appreciate it. This represents a place we did a lot of water jet research. You can see the jet coming out the end. That's back in here coming out. This is 150 GPM at 10,000 PSI. We're going to use it for firefighting, but we had problems with knocking down buildings and people. Cool. Well, thank you. And any questions, I'd be happy to answer.
Many.
Yeah.
It's not just a couple of them.
Sorry, can I question the question after session?
Yeah, you can do that. That sounds good.
Class
That
immediately
sounds
here, and they usually come behind the door. I'm sorry about that.
Okay, no, sorry about
I'm
that.
so sorry.
So, but thank you very much. If you have questions, I'm at 2:15.
Yeah.
Thank you.
Thank you. I didn't know. We didn't know here last week. They came here just